A telescope just revealed something impossible. The universe we thought stretched 14 billion light-years actually spans 93 billion light-years across. The James Webb Space Telescope peered into a patch of seemingly empty sky and uncovered 800,000 galaxies hiding in the darkness. Galaxies that formed when the cosmos was barely 300 million years old. Black holes billions of times more massive than our sun, when they shouldn't even exist yet. Structures stretching tens of millions of light-years across, when there wasn't enough time for them to grow. Everything we believed about the universe's size, its history, its fundamental nature, was incomplete. What you're about to discover will change how you see reality itself. Light takes time to travel. This is one of the most fundamental truths in physics. When you look at something 1 mile away, you're seeing it as it was 5 microseconds ago. Look at the moon and you witness it as it appeared 8 seconds in the past. Gaze at the nearest star beyond our sun, and you're seeing light that departed 4 years before this moment. Every photon crossing space carries within it a frozen image of the moment it began its journey. This isn't speculation or theory. It's confirmed, measured, verified science. The James Webb Space Telescope sits 1 million miles from Earth, suspended at a gravitational balance point where it can stare into darkness without interruption. Its primary mirror stretches 21 feet across, coated in a microscopically thin layer of gold, specifically chosen to catch infrared light. Infrared represents what remains after visible light has been stretched by the universe's expansion. Think of a siren passing you on a highway. As the ambulance speeds away, the sound waves stretch out, dropping to a lower pitch. Light behaves the same way across cosmic distances. As space itself expands, it pulls wavelengths longer, shifting visible light into infrared, ultraviolet into visible, and so on down the spectrum. But Webb isn't simply looking far away. It's looking backward through time itself. The most distant galaxy it has found emitted its light 13.5 billion years ago. Stop and consider what this means. We're seeing this galaxy as it appeared when the universe was only 290 million years old. If you compress the entire age of the universe into a single calendar year, this galaxy formed on January 2nd. The light now reaching our telescope has been traveling through space for almost the entire history of existence. When that light began its journey, Earth didn't exist. Not as a possibility, not as dust, not even as the elements that would eventually form it. Our sun hadn't ignited. The Milky Way was still assembling itself from clouds of cosmic gas. Dinosaurs, humans, every civilization, every thought, every moment of recorded history, all of it came and went while these photons crossed the void. The light we're seeing now is older than our planet, older than our star, older than the structure of our home galaxy. Every image Webb captures is essentially a fossil, a preserved moment frozen in electromagnetic radiation. To capture one ancient galaxy, the telescope gathered photons for almost 10 hours. 10 hours of collecting light that had been traveling for 13.5 billion years. The patience required is almost incomprehensible. Think about it. The telescope stares at a single point in space, darker than anything you can imagine, collecting individual photons one by one, building up an image particle by particle. Scientists use an instrument called a spectrograph to confirm the distance. This device splits light into its component colors, like a prism creating a rainbow. But this rainbow contains secrets. Specific patterns within it reveal exactly how fast the universe has been expanding since the light was emitted. The farther away something is, the more its light has been stretched toward the red end of the spectrum. This stretching is called redshift. The galaxy in question showed a redshift of 14.32, the highest ever recorded for a confirmed galaxy at the time. What this means for us is profound. We're not simply observing distant objects in space. We're witnessing the universe's childhood. We're seeing the first structures that would eventually lead to everything we know. Every star in the night sky, every planet orbiting those stars, every atom in your body can trace its origin back to these early moments. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was forged in stellar furnaces that trace their lineage to this era. But observing these distances creates a problem scientists never fully anticipated. One galaxy in particular has a designation that sounds more like a serial number than a name: JADESGS-Z140. Scientists spotted it in October 2023, then spent months doubting what they saw. It appeared too bright, too large, too developed for something that shouldn't exist yet. The conventional models of galaxy formation simply didn't allow for something like this to appear so early. When astronomers pointed Webb spectrograph at this galaxy in January 2024, they confirmed what they feared and hoped for simultaneously. The object sits 13.5 billion light-years away, formed just 290 million years after the Big Bang. That places it in an era cosmologists call cosmic dawn, when the first stars were supposed to be just flickering into existence. Emphasis on supposed to be. Here's the fundamental problem that keeps astronomers awake at night. This galaxy measures over 1,600 light-years across. That might sound tiny compared to modern galaxies like our own Milky Way, which spans 100,000 light-years. But for its age, it's enormous. It contains several hundred million times the mass of our Sun, all packed into young stellar populations. The light signature is unmistakable. These are stars, confirmed by spectral analysis. Newly born stars blazing with ultraviolet radiation, hot and massive and brilliant. Theoretical models predicted that early galaxies would be small, dim, simple collections of perhaps a few million stars at most. The universe at 290 million years old shouldn't have had time to build anything substantial. Gravity works slowly. Gas clouds collapse gradually. Stars form over millions of years. Dark matter halos, the invisible scaffolding that holds galaxies together, need time to accumulate enough material to seed galaxy formation. Each step in this process has a minimum duration determined by the fundamental laws of physics. Yet there it sits in Webb's images, bright enough that the telescope could detect it, even if it were 10 times fainter. This detail terrifies and excites astronomers in equal measure because it suggests this galaxy isn't an anomaly. If one galaxy exists at this distance with these properties, dozens more probably hide in regions Webb hasn't surveyed yet. And indeed, the team found a second galaxy nearly as distant, labeled JADES-GSZ141, two record-breaking galaxies in the same field of view, both showing properties that contradict standard cosmological models, both producing starlight at rates that should be physically impossible for their age. What makes researchers especially uneasy is the chemical composition. When they analyzed the spectral lines, they found not just hydrogen and helium, the primordial elements created in the Big Bang, but heavier elements, carbon, oxygen, nitrogen. These atoms only form inside stars through nuclear fusion, then get spread through space when those stars explode as supernovae. That means an earlier generation of stars must have already lived and died before this galaxy even formed. The timeline keeps getting pushed backward into territory where our models lose their explanatory power. One astronomer described finding this galaxy as equivalent to excavating a smartphone among ancient Roman ruins. The technology is too advanced for its era. The structure is too sophisticated. The brightness is too intense. Everything about it suggests a level of development that shouldn't be possible given the available time. This discovery forced scientists to extend humanity's view into the cosmic past by roughly 40% during Webb's first 18 months of operation. We're now looking 40% deeper into time than we'd ever seen before. The question nobody can answer with confidence is this: if galaxies this massive existed this early, what else are we fundamentally wrong about? Here's where the universe stops making intuitive sense. Light travels at 186,000 miles per second. Nothing in the universe moves faster. This is confirmed by every measurement we've ever made, tested in countless experiments, verified through observations of distant supernovae and the behavior of subatomic particles. It's as close to an absolute law as physics gets. In 1 year, light covers about 6 trillion miles. We call this distance a light year. Multiply that by the universe's age of 13.8 billion years, and you should get how far light can travel since the Big Bang. The answer should be 13.8 billion light years. Simple mathematics, straightforward logic. Except that answer is completely, fundamentally wrong. The actual edge of the observable universe sits 46.5 billion light years away in every direction. The total diameter measures 93 billion light-years across. We live in a sphere of space nearly 7 times wider than the distance light could possibly travel in the universe's lifetime. This isn't a mistake in calculation. It isn't an error in our telescopes. It's something far stranger. It's expansion. Space itself is stretching. This is the hardest concept to grasp because we have no everyday experience with it. Imagine drawing dots on a deflated balloon with a marker. Now inflate the balloon. The dots move apart from each other even though they're not traveling across the balloon's surface. The rubber between them is growing. Space works exactly the same way. Galaxies aren't flying through space like rockets. Space is carrying them apart. When a distant galaxy emitted light 13.5 billion years ago, it was much closer to us than it is now. That galaxy has been moving away from us during the entire time its light has been traveling toward us. By the time that ancient light finally reaches our telescopes, the galaxy that emitted it has drifted to a current distance of roughly 46 billion light years. Think of it like running on a treadmill towards someone standing ahead of you. While you run forward, the treadmill pulls you backward. You might eventually reach them, but by the time you do, they'll be farther away than when you started running. Light does the same thing, fighting against cosmic expansion as it travels through space. Here's what makes this deeply strange and profoundly unsettling. Regions of the universe exist beyond 46.5 billion light years. We know they're there because space extends in all directions, potentially infinitely. The observable universe represents only the portion where light has had enough time to reach us since the Big Bang. Beyond that boundary, galaxies shine, stars explode, black holes consume matter, planets orbit their suns. We just can't see them. We will never see them. The expansion rate is accelerating. This was confirmed in 1998 through observations of distant supernovae, a discovery so shocking and unexpected that it earned 3 scientists the Nobel Prize. This acceleration is caused by something called dark energy, which comprises approximately 68% of everything that exists. Dark energy's nature remains one of the greatest mysteries in physics. We know it exists because we can measure its effects, but we don't know what it is. Dark energy has a peculiar property. Its density remains constant as space expands. In normal matter, density decreases when volume increases. If you have 10 particles in a cubic meter and double the volume, you now have 10 particles in 2 cubic meters, so the density has halved. Dark energy doesn't behave this way. When space doubles in size, dark energy's density stays the same, which means its total amount has doubled. More space literally creates more dark energy. What this means is staggering. The universe is simultaneously finite in what we can observe and potentially infinite in what actually exists. Every second, the edge of what we can theoretically see grows larger by about 1 light second, but space itself grows faster. Distant galaxies are disappearing beyond our reach right now, at this moment, receding so fast that their light will never reach us no matter how long we wait. And stranger still, different measurements of the expansion rate give different answers. This is called the Hubble tension, and it represents a genuine crisis in cosmology. Webb stared at a patch of sky slightly larger than 3 full moons held at arm's length for a total of 250 hours. The region is designated the Cosmos Webb Field. When the Hubble Space Telescope examined this same area years earlier, it found roughly 10,000 galaxies. Scientists thought that represented a reasonably complete census of what existed in that volume of space. They were wrong by a factor of nearly 80. The final Webb image contains 797,942 galaxies, nearly 800,000 distinct collections of stars, each containing billions or trillions of individual suns. The photograph required combining more than 10,000 individual exposures, each one carefully aligned and corrected for observational errors, instrumental artifacts, and cosmic ray strikes. The data processing alone took months of computational time. To understand the scale, picture printing the famous Hubble Ultra Deep Field on a standard sheet of paper. To show the Webb image at the same level of detail, you would need to print it 13 feet tall by 13 feet wide, a wall-sized mural of cosmic history. Every single point of light in this image tells a story spanning billions of years. Some galaxies in the image formed 12 billion years ago, when the universe was young and chaotic, still settling from the violence of its birth. Others took shape relatively recently in cosmic terms, just a few billion years back. The catalog includes measurements for each galaxy's distance, brightness, total mass, and star formation rate. Scientists can now track how galaxies evolved across 98% of cosmic time, from the earliest moments when stars first ignited to the modern era. What makes this image revolutionary isn't simply the number of galaxies, it's the distribution. The galaxies aren't scattered randomly like salt spilled on a table. They cluster along invisible threads, They gather at intersections where multiple threads meet. They avoid certain regions entirely, creating vast empty zones. The pattern reveals the cosmic web, the largest structure in the universe, a sprawling network of dark matter filaments connecting every major concentration of mass in the observable cosmos. Webb's infrared vision pierced through cosmic dust that had hidden entire populations of galaxies from previous surveys. What appeared empty in visible light blazes, with activity in infrared. Dusty regions where new stars form appeared dark to Hubble, but shine brilliantly for Webb. Ancient galaxies whose light has been stretched into wavelengths human eyes cannot detect suddenly become visible. Objects Hubble literally couldn't see now fill the frame. The team spent years developing technology to measure properties of 800,000 galaxies simultaneously. Photometry to gauge brightness, morphology algorithms to classify shapes, redshift calculations to determine distances, physical parameter modeling to estimate masses and ages. The resulting catalog represents one of the highest quality datasets in observational astronomy. Scientists released everything to the public: the raw images, the processed data, the complete catalog, even an interactive viewer where anyone with internet access can search for specific objects or explore random patches of deep space. This democratization of data means researchers worldwide can mine the information for discoveries without needing their own telescope time. Before Webb launched, astronomers predicted they would find approximately 10 times fewer galaxies at extreme distances. They estimated that galaxies forming within the first 500 million years would be incredibly rare, perhaps a few dozen in a survey this large. The actual count exceeded predictions by more than a factor of 10. Hundreds of extremely distant galaxies crowded into a cosmic era that should have been nearly empty. Something about early galaxy formation is fundamentally wrong in our theoretical models. The Big Bang happened 13.8 billion years ago. This is confirmed by multiple independent measurements: the cosmic microwave background radiation, the abundance of light elements like helium and deuterium, the observed expansion rate, and the ages of the oldest stars. After the Big Bang, the universe was remarkably smooth and nearly uniform. Tiny density fluctuations existed, quantum ripples frozen into the fabric of space during a period of exponential inflation. But matter was spread almost evenly throughout space. Gravity amplifies these fluctuations over time, pulling matter into clumps that eventually become stars and galaxies. This process should be slow, predictable, and gradual. Current models can estimate with reasonable precision how quickly the first structures could form. Gas needs time to cool enough for gravity to compress it into dense clouds. Dark matter halos need to accumulate sufficient mass to attract ordinary matter into their gravitational wells. Stars need to ignite through nuclear fusion and produce the heavy elements that will seed future generations of star formation. Each step in this cascade requires millions of years minimum. The mathematics adds up to a clear prediction about how many galaxies should exist at any given cosmic age. Webb found 10 times more galaxies in the early universe than those predictions allowed. Not 10% more, not twice as many, 10 times more. Researchers checked the instruments for calibration errors. They verified the measurements using independent methods. They examined the data for systematic biases or processing artifacts. Everything confirmed the same impossible result. Within the first 500 million years after the Big Bang, the cosmos was absolutely teeming with galaxies. Bright galaxies, massive galaxies, galaxies containing billions of solar masses worth of material. The universe was producing vastly too much light too early. It had barely 400 million years to form structures containing 1 billion times the mass of our Sun. We don't know how to make that happen with current physics, with our current understanding of how matter behaves under gravity, with our current models of star formation efficiency. One explanation suggests that stars formed far more efficiently in the early universe. Perhaps gas collapsed faster because the cosmos was denser overall, with everything compressed into a smaller volume. Perhaps gravitational collapse worked differently when space was more compressed and the universe hadn't expanded as much. Perhaps environmental conditions unique to that era allowed star formation to proceed at rates physically impossible in the modern universe. But this is speculation layered on speculation, not confirmed theory backed by experimental evidence. Another possibility involves dark matter physics. Different theoretical models of dark matter predict different abundances of dark matter halos in the early universe. If dark matter behaves differently than the standard cold dark matter model assumes, it could create conditions that dramatically accelerate galaxy formation. Measurements from Webb might eventually help distinguish between competing dark matter theories by showing which one best matches the observed galaxy distribution. What troubles astronomers most is the consistency of the surprise across multiple independent surveys. It's not one anomalous galaxy that might be explained away as a statistical fluke or measurement error. It's hundreds of galaxies across multiple surveys, examining different regions of sky using different instruments and different analysis techniques. Every deep field Webb examines reveals the same disturbing pattern. Far more galaxies exist in the early universe than should be possible. The implications cascade outward through our entire understanding of cosmic evolution. If galaxies formed this abundantly in the early universe, they must have influenced their surroundings far earlier than expected. They would have started reionizing the universe sooner, stripping electrons from neutral hydrogen atoms and making space transparent to light. They would have enriched space with heavy elements faster, enabling the formation of later generations of stars and planets. They would have seeded the formation of larger structures earlier, affecting the growth of the cosmic web itself. The entire timeline of cosmic evolution might need substantial revision. Every textbook chapter on the early universe might be incomplete or partially incorrect. And some of those early galaxies possess properties that border on physically impossible. Astronomers discovered galaxies in the infant universe that weigh 100 times more than theory permits. These objects appeared so impossible, so thoroughly incompatible with standard cosmology, that researchers initially called them universe breakers. The name wasn't hyperbole. Their existence seemed to violate the fundamental laws governing how structure forms in an expanding universe. The problem comes down to time and the speed limit imposed by physics. Building a massive galaxy requires accumulating enormous amounts of matter through a series of steps that each have minimum durations. Dark matter must collapse into a gravitational halo first, a process that takes millions of years. Then ordinary matter falls into that halo, attracted by its gravity. Then the gas cools and fragments into clouds dense enough to form stars. Then those stars are born, live out their lives, and die. Then the heavy elements they produce through fusion seed the next generation of stellar formation. This cycle repeats over and over as the galaxy grows in mass and complexity. Each step has a minimum duration determined by fundamental physics. You cannot compress gas faster than the speed of sound through that gas without creating shock waves that heat it back up, preventing further collapse. You cannot form stars instantaneously. You cannot skip the waiting period while stellar evolution proceeds at its own inexorable pace. The standard model of cosmology calculates exactly how massive a galaxy can possibly become at any given cosmic age, given these constraints. Some early galaxies exceeded those theoretical limits by factors of 10 to 100. They appeared to contain more stars than should be physically possible given the time available since the Big Bang. Their brightness suggested stellar populations too large for the cosmic era in which they formed. Their mere existence challenged foundational assumptions about how the universe works. Scientists scrambled to explain this astronomical crisis. Perhaps the galaxies weren't as massive as they initially appeared. Perhaps bright, active galactic nuclei, supermassive black holes, consuming matter and radiating tremendous energy, made them look bigger and brighter than they actually were. Perhaps the light came partially from these black holes, rather than entirely from stars, inflating the apparent stellar mass. Recent deeper analysis suggests this explanation is partially correct, though not completely sufficient. Some of the so-called universe breakers do harbor extremely bright, active galactic nuclei that inflated their apparent mass in initial observations. When astronomers carefully account for black hole contributions and reanalyze the data with more sophisticated models, the galaxies shrink to more reasonable sizes. They're still massive for their age, pushing the boundaries of what models predict, but they no longer shatter the theoretical framework entirely. However, even after these corrections, roughly twice as many massive galaxies exist in the early universe as standard models predict. The discrepancy has narrowed dramatically from a factor of 100 to a factor of 2, but the problem hasn't disappeared. It's merely become less catastrophic. Something about early galaxy formation still remains fundamentally unexplained. One research team compared Webb's observations to Hubble's decades-long census of galaxies at similar distances. Hubble had been observing for more than 30 years, building what scientists believed was a representative sample of galaxy populations at various cosmic epochs. If the standard cosmological model was correct, Webb and Hubble should see broadly similar distributions of galaxy masses at any given distance. Any increase in Webb's counts should come primarily from detecting fainter galaxies that Hubble missed due to sensitivity limitations. Instead, Webb found far more bright, massive galaxies than Hubble's data suggested should exist. This inconsistency points either to environmental differences in the early universe that we don't understand, or to fundamental gaps in our theoretical understanding of how efficiently matter converts into stars under the extreme conditions present in the first billion years after the Big Bang. The research continues with increasing urgency. Each new observation refines the puzzle. Each measurement narrows the range of possible explanations. What remains absolutely certain is that massive structures appeared far earlier than our best theories predicted. And at the centers of some of these impossibly early galaxies lurk monsters even more perplexing than the galaxies themselves. A supermassive black hole sits at the heart of galaxy GNZ11, one of the most distant galaxies ever observed. This black hole existed when the universe was only 430 million years old, barely 3% of its current age. Its mass equals millions or possibly billions of times the mass of our Sun. That shouldn't be possible under any conventional understanding of how black holes form and grow. Black holes form when massive stars collapse at the end of their lives. A star needs to be at least 20 times more massive than our Sun to create a black hole when it dies. The resulting black hole typically weighs 10 to 100 times the Sun's mass, sometimes more for the most massive progenitor stars. From that initial mass, the black hole can grow by consuming gas, dust, and other stars that venture too close to its gravitational grip. But this process takes time, billions of years of gradual accumulation. Even if a black hole formed immediately after the Big Bang and consumed material continuously at the maximum possible rate allowed by physics, it couldn't grow to billions of solar masses by 430 million years after the universe's birth. The physics of matter falling into black holes imposes strict theoretical limits on growth speed, called the Eddington limit. Exceed this limit, and the radiation pressure from infalling matter blows away additional material before it can be consumed. Yet there it was in Webb's data, undeniable and impossible to explain away. The telescope detected extremely dense gas surrounding the black hole, a clear signature of rapid accretion. The black hole was actively feeding, pulling matter inward at tremendous rates. Spectral analysis revealed emission line patterns that only appear near supermassive black holes, consuming gas and radiating across the electromagnetic spectrum. This galaxy isn't unique or even particularly unusual in Webb surveys. The telescope has discovered multiple supermassive black holes in the early universe, some appearing even more massive than expected for their cosmic age. Each discovery deepens the mystery of how these objects grew so large so quickly when every physical process we understand suggests they shouldn't exist yet. Several theories attempt to explain this cosmic puzzle. One possibility involves hypothetical objects called dark stars, theoretical stellar-like objects powered by dark matter annihilation rather than nuclear fusion. These dark stars could theoretically grow to millions of times the mass of our Sun before collapsing directly into massive black holes, providing an enormous head start on growth. Another theory suggests that in the extremely dense early universe, gas clouds could collapse directly into massive black holes without forming stars first. If conditions were exactly right, a cloud containing 100,000 solar masses might compress straight into a black hole of equivalent mass. This process, called direct collapse, has never been observed, but mathematical models show it's theoretically possible under very specific conditions. A third explanation involves collisions and mergers. If smaller black holes merged frequently in the crowded early universe, they could build up mass faster than accretion alone allows. Gravitational wave detectors like LIGO have confirmed that black hole mergers definitely occur in the modern universe. Perhaps they happened far more often in the past when galaxies were closer together and interactions more common. What makes these supermassive black holes especially important scientifically is their role in galaxy evolution. Black holes don't just sit passively at galactic centers like cosmic drain holes. They blast out enormous amounts of energy as matter spirals inward through the accretion disk. This radiation heats surrounding gas and can either trigger new waves of star formation or shut it down completely by heating gas too much for gravitational collapse to occur. Supermassive black holes essentially help regulate how galaxies grow. Finding them so early in cosmic history means they influenced cosmic evolution from nearly the very beginning. Their presence could potentially explain some of the unexpected galaxy properties Webb keeps discovering in the early universe. But before these black holes existed, something even stranger might have burned in the primordial darkness that filled the universe before the first normal stars ignited.